All right, so in the last lecture we talked about how to prepare alcohols, and now I'm going to start talking about reactions of alcohols. And once we've made them, what can we do with them? Okay, so some of this, once again, is review, but you're going to learn some new reactions in today's lectures as well. We know that we can convert alcohols into alkyl halides. We studied that back in Chapter 10. It would be great to have those notes available to review over. If we wanted to convert a tertiary alcohol into a alkyl halide, we can use an SN1 type mechanism using hydrochloric acid or hydrobromic acid, and that's because it goes via a carbocation intermediate, okay, as I'm showing you below. However, this type of reaction doesn't work very well with primary or secondary alcohols because making those types of carbocations takes a while because they're not as stable and therefore lower yields. So another way to convert alcohols into halides is to add thionyl chloride or phosphorus tribromide or phosphorus bromide, and that's going to go via an SN2 reaction. But before I get into that, I want to review over the mechanism real quickly. When we have here, when we do a tertiary alcohol, we react it with a strong acid, and that strong acid will help protonate the alcohol to make it into a better leaving group. You can see here that now that hydroxide, which is a really poor leaving group, is converted into water, which is a good leaving group. And once that water leaves, we're left with a carbocation. Now, what's the hybridization of a carbocation? sp2. What's the molecular geometry? Trigonal planar. Fantastic. Good. Which means the incoming nucleophile can attack from both sides, right? So if you end up having a chiral center, you will end up with how many products for SN1? You will end up with 2 products, right? Because this reaction comes in, and they're not necessarily a racemic mixture. Remember that this side here, the retention side, is kind of blocked by the leaving group. And so the nucleophile will have an easier chance coming from the back. So you'll have more inversion product than you would the retention product, right? Because this kind of is still lingering around the carbocation, per se. So not necessarily a racemic mixture. It's usually unequal. Once again, a lot of review there. So if you're feeling like, ooh, I don't remember that too much, there's a great figure in your textbook that shows the ratio of products for SN1, the inversion versus the retention product, and approximate ratios. Okay. Now, for primary or secondary alcohols, we have to use different reagents, like I said before. And as you know, and hopefully remember, that the hydroxide ion itself is a very poor leaving group. Okay. A very poor leaving group. And so what we have to do is we have to use these special reagents like thionyl chloride and phosphorus bromide. And the reaction of an alcohol with thionyl chloride or phosphorus bromide converts the alcohol into a much better leaving group. That's the goal here. So we use these reagents to convert the hydroxide into a much better leaving group. Okay? And so I'm not going to go through the full mechanism here, but I do show you the intermediates. I did want to show you the structure of thionyl chloride. Right? And that sulfur there is very partial positive, right? So you can kind of see here how those electrons come up and attack that sulfur. And what ends up happening is, this is more advanced stuff because we'll eventually get to nucleophilic acyl substitution in a while, but in chapter 21. But these electrons come up to here, but eventually they come back down to regenerate the carbonyl and then kick off the chlorine leaving group. Okay? That's a lot right now. Like I said, once we get to that chapter, and I'll show you the intermediates, and we'll do it slowly. But what you end up having in here is a chlorosulfite intermediate. And this is going to end up being a really good leaving group, because what's going to happen is that the chloride's going to come in and do backside attack. Remember, this is an SN2 mechanism, because we're working with primary and secondary alcohols to start with. This backside attack, that means these electrons come here to form a double bond between sulfur and oxygen. We kick off the leaving group. We're able to make sulfur dioxide and chloride, and now our new alkyl halide, which has inversion stereochemistry. Remember, SN2 only makes one type of product, and that's the inverted product, because it does backside attack. And there's no carbocation intermediate here. And so the reason why this is extremely favored is because we form many products. And we would say that this is entropically favored, because we know, based on the second law of thermodynamics, that the universe just wants to go into a more entropic state, so more entropy, and that's going to be the driving force for some of our reactions that we study. If we get to make lots of little tiny products, that's really favorable for a reaction. It wants that disorder. Okay? Likewise, if you react with phosphorus bromide because you want the alkyl bromide rather than the alkyl chloride, then you're going to make a better leaving group, and this is a dibromophosphite leaving group, and so these oxygens going to attack the phosphorus and then kick off the bromine, and then the bromide will attack, backside attack, kick off this leaving group here, which is a very stable leaving group on its own, and then we get that inverted alkyl bromide. So once again, I'm kind of oversimplifying the mechanism for you. Make sure you even practice this mechanism, though, just because it'll help you to remember, what's going on, what type of mechanism is happening. I need to know the mechanism because I need to know the stereochemistry, right? So be careful with that. Now, in Chapter 11, I introduced something, and I think I maybe mentioned it in Chapter 10, but converting alcohols into tosylates. If we react an alcohol with para-toluene sulfonyl chloride, so this is your tosyl group, we need to do it in pyridine. That's critical here. It acts as a solvent and a weak base. It yields something called an alkyl tosylate. Okay? And this is this little abbreviation. What's really interesting about this is that it doesn't affect the chirality of the carbon atom. So for example, let's say this alcohol had a chiral center, so that's why it has an asterisk next to it. Because the reaction is between the oxygen and the sulfur, and once again, it has a very interesting mechanism I'm not going to go into right now. If you're interested in it, you can always come to office hours and I'll talk to you about it. We don't have the time for it right now. Later on, future slides, we will in those chapters. But anyway, so that it's because the reaction between the oxygen and sulfur, nothing's happening to the R group. So the configuration at the chirality center is maintained. Okay? And although when we did Chapter 11, we talked about alkyl halides, reactions of alkyl halides, you can also have alkyl tosylates. They behave very much the same way as alkyl halides. And that's because tosylates are fantastic leaving groups. They're actually even better than halogens. They're very good leaving groups. And the reason for that is, why do you think they're great leaving groups? It's because when they leave, they're stabilized by a resonance. Okay? Makes it very stable. It wants to leave, right? Because it wants to be stabilized by resonance. And one of the most important reasons, you're like, okay, why don't I just use an alkyl halide? Why do I have to do this tosylate reaction? One of the most important reasons for using tosylates in SN2, it's all about the stereochemistry. Okay, so If you're trying to manipulate the stereochemistry, then you might want to use tosylates in your multi-step synthesis. Here's why. Okay? If we go from an alcohol and we do the normal alkyl halide route and then do an SN2 reaction, originally this has R stereochemistry, right? 1, 2, 3. It looks like S, but the hydrogen is going forward, so it's actually R. When we do the phosphorus bromide conversion, that's an SN2 mechanism in itself, correct? Good. It is. So therefore, the stereochemistry is what? Inverted. We have inversion. And then let's say I don't want the halide, right? I want to do an SN2 reaction with sodium methoxide. I have this really great nucleophile. It comes and attacks, does backside attack. Once again, I have inversion of stereochemistry. So I started with R configuration. I actually ended up with R through this whole process. But let's say I'm trying to design something that doesn't give me R configuration, but eventually gives me S in the end. Well, in that case, if you want to manipulate your reaction that way, you shouldn't convert it to an alkyl halide. You should react it and make it into a tosylate. And so here you react it with para-toluene sulfonyl chloride, so you can use this abbreviation. You must use pyridine for it. It involves the mechanism. We need that weak base there. And you can see here that it started with R. When you do the tosylate reaction, it didn't affect it. It's still R. However, because it's still R, when we do the second SN2 reaction, we definitely get inversion. And so I end up with S stereochemistry in the end, and that's how I can distinguish between, for example, ethyl R 1-methyl-heptyl ether versus ethyl S 1-methyl-heptyl ether. Okay? So be careful with that, especially when I ask you to do multi-step synthesis and you're like, I need to get the stereochemistry. How can I do it? You know, think about your leaving groups. They're important too, and you can manipulate stereochemistry using a halide versus a tosylate. Once again, we can do other reactions with alcohols. So we can not only make alcohols from alkenes, we can make alkenes from alcohols. So the other way around. This type of reaction is called a dehydration reaction. There's several ways that you can do it. One way to do it is to do an acid-catalyzed dehydration. And if you have a tertiary alcohol, this is maybe the way to go. And you'll notice that when we do this reaction, that 2-methyl-2-butene is the major product. Why do you think that is? Just looking at the products. It's more substituted. Good. Now, if you want to make an alkene from a secondary alcohol, don't use these conditions, okay? Or from a primary alcohol. It's really hard to dehydrate primary alcohols, by the way. You're going to end up having to convert it into an alkyl halide and then do an elimination or something like that. But secondary alcohols, it would require very harsh conditions, and most molecules wouldn't survive. So this is only very useful for tertiary alcohols. And like I said, it's very impractical to do a primary alcohol. It's just not going to happen. Okay? And the reactivity and what we see in our results that the more substitutes formed is based on the fact that we're seeing a carbocation intermediate. The type of mechanism, you've already seen this before in Chapter 11, this mechanism follows an E1 mechanism. Remember, when we make alkenes, you're doing some sort of elimination reaction, right? To make an alkene, eliminate a small molecule. And in this case here, this E1 mechanism, remember what kind of stereochemistry did E1 follow? What kind of rule did E1 follow? We called it Zaitsev's rule. Remember, this is from Chapter 11. So once again, more review. Hopefully you've been studying that. So Zaitsev's rule, E1 mechanism. And Zaitsev's rule means the more substituted alkene forms. Okay. Let's go into the mechanism in a little bit more detail. Okay. I'm choosing a different starting material. because I want to make sure I illustrate stereochemistry. So this is an acid-catalyzed dehydration. Anytime you see acid-catalyzed, you think hydronium ion. So you want to draw your hydronium ion as the electrophile. Like I said, I always like to draw my starting electrophile in blue, my starting nucleophile in red, and my new bonds in green. So this oxygen is the one that's most attracted to the hydronium ion. So it's going to attack that, pull off a proton. These two electrons go on to the oxygen to form water. And now we have a protonated alcohol here. With the what kind of formal charge on oxygen? With a +1 formal charge. Okay, so we have an intermediate here. And that particular intermediate, this group that we just formed is water. And water is a good what? It's a good leaving group. So hopefully you've already predicted it's going to leave, right? So these two electrons are going to go onto the oxygen to kick off water. And what kind of intermediate are you going to form? You're going to form a carbocation intermediate. Fantastic. So now we have a carbocation intermediate, right? And I'm going to also draw in some hydrogens here because we're going to have to do an elimination. Now we have water present, right, in our reaction mixture. And water is amphoteric, which means it can act as an acid or a base. In this case, it's going to act as a base. It's going to pull off a proton. And it's going to mainly pull off this proton. These two electrons are going to go here to form the more substituted alkene. This reaction is in equilibrium, by the way. So the double bond is going to go here, and this is the major product. A lot of times students are like, well, Dr. P, couldn't it also come over here and make the double bond over here? It could, but that'd be a very minor product for E1. Right? Because it wants to form the more substituted alkene. In addition, when water does that, it pulls off that hydrogen to regenerate the hydronium ion. So we regenerate the acid catalyst. And anytime I give you an acid catalyzed reaction, you want to follow its mechanism all the way through to see if you do regenerate the catalyst. Same thing if it's a base catalyzed reaction. That way you know if you do, then you probably predicted the mechanism correctly. You can always cross your check yourself that way for those catalyzed reactions. Now back in Chapter 11 we talked about with E1 that the more substituted alkene forms. And that all came from when we talked about in Chapter 7.6, this concept of hyperconjugation. And if you don't remember it, then go back in the textbook and read through it again or look through my slides or both, right? And that's the idea of like the more substituted the alkene is, the more stable it is. And that's because there's more orbitals to help kind of share those electrons in a sense, right? That's why we call it hyperconjugation, because it's not actually conjugated. Because the orbitals here are sp3, they're not like p orbitals, but they do kind of overlap to make like a more stable molecular orbital per se, because molecular orbital is going to give you the true picture of it. Whereas if it was just hydrogens here, hydrogens only have 1s atomic orbitals, they don't help to stabilize that double bond too much. Okay, so it all has to come back to hyperconjugation. And we talked about that in Chapter 7.6. So this was for tertiary alcohols. For secondary alcohols, we use a different type of reagent called phosphorus oxychloride. We do this in an amine solvent, so in the presence of a weak base. And we can dehydrate secondary, and you can also dehydrate tertiary, because if you don't want to heat your sample up, at least you can run this reaction at low temperatures. It follows an E2 mechanism, though, and we'll go through that in a second. But what I wanted to point out is its reactivity. Tertiary still will be the best option here, but you can do secondary. Once again, it's really difficult to dehydrate primary. So you might need to convert the alcohol into an halide and then do some sort of elimination reaction after that. So this really is only useful for secondary and tertiary alcohols, phosphorus oxychloride. Okay, let's go ahead and do an example. A type of mechanism. And I'm definitely going to show you a lot of stereochemistry here, because if you remember from Chapter 11, that E2 mechanisms are quite particular. Okay, reacting with phosphorus oxychloride, which is going to act as your electrophile. So I'm going to go ahead and draw that particular structure here. Okay. And which atom do you think is the most electrophilic? What do you think the oxygen's most attracted to? The oxygen is definitely attracted to the phosphorus, right? Because that phosphorus has all these chlorines and oxygen attracted to it. So we are going to attack the phosphorus. It's going to kick off one of the chlorines. Like I said, I'm kind of simplifying that particular part of the mechanism. And let's go ahead and draw the intermediate that we make. So nothing has happened here. So I'm going to just maintain that stereochemistry as is. This oxygen still has that proton, lone pair. Now we have a new bond between oxygen and phosphorus. And I'm just going to abbreviate that as POCl2, because eventually we're just going to end up kicking it off as a leaving group. And there's a +1 formal charge on that oxygen. So this is the intermediate we have. Now I said we're running this under like a basic conditions, like we have some sort of amine in there. So I'm going to add pyridine. Which helps not only with solubility, but also with doing these types of like deprotonations of the intermediate. So it's going to pull off that proton and put those electrons onto the oxygen to give us this particular intermediate here. So let's go ahead and draw it. And as I'm deriving mechanisms from here on out, if you haven't done so already, try to beat me to it. You know, you've seen a lot of patterns before. You hopefully understand the basics of organic chemistry and electron flow. So you can kind of predict, okay, what's my nucleophile? What's my electrophile? You know, what do I need to do here? How are the electrons behaving? And knowing that information, knowing that chemical intuition is going to help you big time. So the more you can practice during lecture, kind of predicting the mechanism before you see me do it, the better off you'll be. Okay? The more prepared you'll be, because you've already been practicing and actively learning through it. You know, and then if you get it wrong, then you're like, okay, now I know what to do. Now remember that with E2, I'm going to kind of like step away from the mechanism a little bit here and kind of just review and jog your memory. With E2 mechanisms, they're stereospecific. Remember, I mean, just like E1. E1 wants to make the more substituted alkene, but it's different for E2. E2 mechanisms are just like all one step. Once the elimination starts, there's no carbocation intermediate, it just goes, right? And so therefore, we always had to be what type of geometry? Anti-periplanar. And when we mean by anti-periplanar, is if we had, for example, an open chain structure, then the leaving group and the proton that's being protonated, or deprotonated, removed, need to be anti with respect to each other. Okay, so if you know you have an E2 mechanism and it's an open chain structure, then you need to build your Newman projection so that you can figure out what your stereochemistry is after you form your double bond. Now in this case here, I have a cyclohexane structure. So drawing Newman projections of cyclohexanes can be tricky, and therefore we draw chairs. And when we draw our chairs, we need to have them trans 1,2 diaxial, the leaving group and the proton that's being deprotonated to form the double bond. And so it's important that we studied that back in Chapter 4 when we talked about stereochemistry of cycloalkanes. It's important that you know how to draw chair conformation in order to predict E2 products. Okay? So what I'm going to do here is I'm going to convert this into a chair on my own, right? You know, when you're doing a mechanism, I might just say predict the products. You know, and I don't tell you to do the mechanism, but you kind of need to do it, especially for this case here, to really know your stereochemistry. So I'm just going to draw a chair. And I'm going to number the ring. It doesn't matter how you number it, but I will number this 1, and this 2, and this is 3. Okay? And in this case here, I have, you know, carbon 1, 2, and 3, just being consistent. And I'm just going to draw the bonds here. Okay. So in this case here, it's like that. Make sure my bond angles are good. So in this case here, is the methyl group on the top face or bottom face? It's on the bottom face. Good. Is the OPOCl2 on the bottom face or top face? It's on the top face. Good. And the hydrogen's on the bottom face. And then we have hydrogens here and here. Now, I need to be trans 1,2 diaxial. And right now, is this in the axial position? No. So what should I do? I need to ring flip, right? So let's go ahead and ring flip it. And remember when I did that, this top part here always says the nose of your dog, right? It becomes the tail. And we're numbering clockwise, so I just continue to number clockwise. So therefore, let's go ahead. There we go. On carbon number 1, the methyl group is on the top face or bottom face. It's on the bottom, good. OPOCl2, top face or bottom face? Top face, it's bold, so it's coming at me. So we say that's the top face. And then the hydrogens. There we go. Now, what students will make the mistake here is they'll say, okay, well, I want to make the more substitute double bond, right, because it's more stable. You can't do that with E2 anti-periplanar because this is trans 1,2 diaxial with respect to our leaving group. So we can't pull off that particular, that group there. So we need to pull off this hydrogen here. And so that base is going to come in, that's a pyridine. Pull off that proton. These electrons are going to come here to form a what type of bond between carbons 2 and 3? A double bond. And then you're going to kick off your leaving group. So in the end, this is carbon 1, 2, and 3. I'm going to have a double bond between carbons 2 and 3. And that's the only product I'm able to make. I'm not able to make the more substituted products. So please, please be careful of stereochemistry. Especially with E2 reactions. And the ACS study guide has some great examples of where you'll need to build a Newman projection or you'll need to do a chair conformation in order to predict the correct product with the correct stereochemistry. All right, so just kind of digest through that. Maybe practice it on your own again, kind of try to derive your own chair conformations. I think that's the hardest part for students. And if you feel really weak on that because it's been a while or it just never clicked with you in 12A, please come see me and I can help practice chair conformations with you, converting from skeletal structures to chairs, because I know that can be really challenging. It was hard for me as a student, so I completely empathize with that. Just take some practice and I can teach you some tricks. Also, maybe going back and reviewing over Chapter 4 again, just that particular part of Chapter 4, if you want to, will be great practice for you. Okay, great review. Now, we can also convert alcohols into esters. I'm going to save this, though, a little bit later for Chapter 21. But you can see here I can go straight from a carboxylic acid into an ester. We'll talk about that Fischer esterification reaction. We can also go from what's called an acid chloride, so we convert a carboxylic acid to, acid chloride using thionyl chloride, very similar to what you saw already, and then using an alcohol to make the ester. And so these will be very common reactions you're going to use in the future, and because we always, a lot of molecules, pharmaceutical drugs, and biochemical structures have esters in them, so it's important that we know how to synthesize them. Let's go ahead, pause the video, and I want you to try to predict the product of the following reaction below. And in addition, I know I always say predict the product or predict the products, but many times you might have to do the actual mechanisms for it. So if you need to, write that down. And remember, for exams, I'm always going to provide you scratch paper. Knowing your mechanisms, or at least a simplified version of it, will help you greatly with predicting products. Hopefully you've had a chance to do it. Let's check your work. The first step looks like we're adding para-toluene sulfonyl chloride. What is that going to do? That's going to replace this and make this hydroxide into a better leaving group without affecting the stereochemistry. So I'm just going to do the first step here, even though we're going to take it further. I'm not going to play with that stereochemistry. It stays the same. Okay? And then after that, sodium methoxide, and this is its conjugate acid. What type of mechanism? SN2. It's a very strong nucleophile. Now, a lot of times students get upset and say, Dr. P, I see methanol in there. That's polar protic. Don't worry so much about the whole polar protic thing. Remember, this is also the conjugate acid of sodium methoxide. So it's not like I'm adding water in there, for example, which is very polar protic or whatnot, to really slow down the mechanism. But the conjugate acid will be in there. And yes, it does slow it down a bit, but the fact that it's a strong nucleophile, secondary alkyl tosylate, we're definitely doing an SN2 reaction, which means what about the stereochemistry? It means that it's going to be inverted. So the hydrogen is going to come at me, and the methoxide is going away from me. Okay? So inversion of stereochemistry. I hope you got that answer right. If you didn't, then please come see me. I want to try to help you out there. So just like we can do reduction reactions of carbonyls, we can oxidize and go backwards to oxidize alcohols into carbonyl compounds. And this can be done with all sorts of reagents, so make sure you start learning those. And when I talk to my students, I always say, have a list of reduction reactions and have a list of oxidation reactions, and know those reagents so that you're just aware of them. Potassium permanganate, chromic acid, sodium dichromate, anything that has lots of oxygens in them are good oxidizing agents. Get it? Okay, good, hopefully. They have lots of oxygen in them, right? So we can oxidize a primary alcohol to a carboxylic acid. There's going to be ways to make it stop at an aldehyde, and I'll get into that in the next slide. You can oxidize a secondary alcohol into a ketone, because you'll have two R groups here. but you can't oxidize a tertiary alcohol. It's just too difficult. So this is a limitation, and this is one of those ones that you should learn, because remember, there's going to be no reactions on your exam, like in predicting products. They'll say, okay, there might be a no reaction on there. So which one do you think it is? You need to know your limitations. If I give you a tertiary alcohol and I say, react that with potassium permanganate, you say, nope, reaction. No way it's going. Okay? Definitely a limitation. Now you may be thinking, well, how am I going to know which one to use, potassium permanganate or chromic acid or sodium dichromate? Well, the choice really depends on the cost. It's all about money, right? The convenience. What do I have laying around in my lab right now at this point in time? I need to do it now. The reaction yield and the alcohol sensitivity. So if your molecule is sensitive to very strong oxidizing agents, you may want to use something that's a little gentler, which I'll show you in the next slide. Okay, so it comes down to those things. And in all honesty, for the most part, it's safe to choose any of them. However, if we want to stop at the aldehyde, we'll have to use a very specific type of oxidizing agent. But you're definitely going to use these quite a bit in your multi-step synthesis. Very useful reactions to know. Okay. A way that we can stop at the aldehyde, though, and use a gentle oxidizing agent, we can use something called PCC. Okay? And that will take a primary alcohol into an aldehyde. It will also take a secondary alcohol into a ketone, so you can use that too, but it is more expensive, and you can see the structure here as well. This is the one that I used a lot in undergrad and graduate school. I noticed that your textbook doesn't talk so much about PCC, and that they're introducing another reagent that I wanted to show you as well, and this is called the Martin peridothenane. And that reagent has a very interesting structure. I'm less concerned about you knowing the structure. Same thing with PCC. I'm okay if you use PCC. I'm fine with that. But if you want to use the Martin, then you need to write the name out on the reagents. You don't have to show the structure. You can do either. I'll accept either. But I know that structure is a little bit tedious. Same thing with PCC. I don't really write the structure down. I just write PCC. Methylene chloride is your solvent here. You want to start including solvents in your synthesis, right? It makes it soluble. And your textbook actually goes through the mechanism in great detail, which I think is fascinating. You should review over it. But I won't test you over the mechanism of this particular oxidation. Oxidations tend to be a little bit crazy, right? They usually involve radicals and that sort of thing. So in my beginning organic chemistry class that I'm teaching here, I don't go into that much detail. Okay? If we wanted to oxidize a secondary alcohol, but let's say something that's sensitive. So you can see here, this is testosterone, so it's a steroid here. And these other functional groups may be sensitive to potassium permanganate or these really harsh oxidizing reagents in their conditions. And so you can use PCC or that Martin reagent to oxidize a secondary alcohol into a ketone. So safe option to use because you get to work at lower temperatures at least with those particular reagents. Okay. This is showing you a basic chromic acid oxidation. Like I said, I'm not going to really test you on the mechanisms, but I always find that knowing the mechanisms or at least being aware of them may help you to remember what you're going to get from them. And so what ends up happening is that an alcohol ends up attacking the chromium, right, the Lewis acid, to forming a chromate ester. And then you're in the presence of base, and so we do a type of elimination reaction. So we pull off this proton, and then elimination to pull off the last proton to regenerate the double bond and kick off the chromic acid. And the mechanism was determined by observing the effects of isotopes on rates. So it's been studied and, quite extensively. And I talk a little bit about isotope or kinetic isotope effects before in previous lectures, and You'll hear me talk about it a little bit more later on. It's like, how do they really know that these mechanisms are happening? So they use isotopes to help do that, and different types of spectroscopy, as well as computational chemistry to predict mechanisms. Okay? Like I said, oxidation reduction mechanisms, I'm not very, particular on, teaching you the nitty-gritty details. I just want to teach you the overall basics so it helps you to remember it and derive it on an exam if you need to, but without giving you all the extraneous information. Now, if you remember, I talked about Grignards, one of my favorite reactions, right? And they're very sensitive to an acidic hydrogen, right? You can't have those around, otherwise you're going to end up making a hydrocarbon and not the carbon-carbon bond that you want it to. Well, there's a way to work around this. Let's say I'm pretty determined I want this to be my Grignard reagent. Then I can't immediately go straight to making the Grignard. I have to protect it. I have to protect the alcohol to prevent other reactions from happening, and without also losing my alcohol functionality. Okay? Because remember, the limitation to a Grignard is that Grignard reagents react with acidic protons or hydrogens. Okay? That's a problem, right? So there is a way to get around it. And this is going to be so important to you, okay? Especially in multi-step synthesis. We have a method for protecting alcohols. Very key in organic chemistry to know your protecting groups. Okay? What we end up doing is we react our alcohol with trimethylsilane. So this is chlorotrimethylsilane. You can also see it as TMS chloride. I'm okay if you use that abbreviation. In the presence of base, in this case here, we're using triethylamine. Very stinky base. It smells like fish, right? And the ether can be cleaved with acid. So once again, we make an ether. We make a trimethylsilyl ether. This is protecting that alcohol. We can do other reactions with it and then deprotect it using acid. Or silicon really loves fluoride. So we're not going to use fluoride in my synthesis, but you might see it in your future if you take an advanced organic chemistry class. But we can regenerate the alcohol, which is great. Okay. So you may be looking here and you're like, Dr. P, okay, I can see the base pulling off the proton to make some sort of alkoxide anion, but eventually these electrons come in and attack a tertiary silicon substrate. This looks like an SN2 mechanism. Does that happen? Yes, it does. This is not carbon, right? Where is silicon at on the periodic table? It is right underneath carbon. So the reaction, I'm going to write down here, occurs because silicon is a third row element and is larger than carbon, and therefore can form longer bonds. So that's the reason why it can occur, which is really convenient for us. And it's one of those bonds that we can easily break, like I said, with acid. You can use the abbreviation TMS instead of drawing the structure out. I'm okay with that because it's just a protecting group when we do this particular reaction. Now, when we do protecting groups, the first thing, there's kind of a procedure to it. For step 1, you introduce the protecting group to block interfering reactions. Like I don't want the Grignard to react with the acidic proton. I want it to react with my carbonyl. The second thing you do is just carry out the desired reaction. So I'm going to run my Grignard with the protecting group in place. And then the third step is to remove the protecting group. And this is not the only time I'm going to talk about protecting groups. I kind of just want to go over the basic procedure with you because you're going to see protecting groups later on. But basically, you put the protecting group on it, you then do your reaction, and then you should be able to remove it. So it's really, it may seem like, oh, you're adding a lot of extra steps, but it prevents you from running undesired reactions or getting lots of mixtures of products and having to purify those later. Okay? Let's go through an example of one. This is an example of a TMS alcohol protection in a synthesis. Right now I have this reagent here, and I eventually want to run a Grignard. So in my multi-step synthesis, I know before I run the Grignard, I have to protect it. So I'm going to react it with TMS chloride, or trimethylsilyl-chloride, in the presence of triethylamine. You need that base in there, and I'm going to look for that when you're doing these types of designs or synthesis designs. Okay? You can see the TMS has protected our alkyl halide. The alcohol is not there anymore, or it's there, but it's being protected, right? Then you go ahead and carry out your reaction. So we're first going to form the Grignard. That's the first step, to make the Grignard reagent. And then you're going to react it with whatever electrophile you want. So in this case, we have an aldehyde. So this group here is going to attack this carbonyl carbon, put those electrons up, make the alkoxide ion intermediate. So if we said carbon 1, this is carbon 2, right? Make the alkoxide ion intermediate, and therefore neutralize with acid to regenerate the alcohol. Now, by doing that neutralization at the very end, it's going to actually combine both of these steps. And we're showing it separately to say, okay, you carried out the reaction, you did it, then you need to remove the protecting group. You may need to add a little bit more acid if it's not completely removed. But I'm okay if you combine both steps and just show the deprotection in the same step. If you want to show them separately, that's also fantastic too. I won't take off. But this acid here is just redundant, right? It does both neutralize the alkoxide ion and remove the protecting group. Okay? So practice that. I think students tend to have some difficulty with that. And so make sure you practice the protecting groups. You're going to see it later on when we protect aldehydes and ketones and that sort of thing. So we'll get into a lot of protecting group chemistry later on. I did want to talk a little bit about reactions of phenols very briefly. We can oxidize them. And remember that hydroxyl group is actually very strongly activating. So chapter 15 and 16. They're great substrates for electrophilic halogenation, nitration, sulfonation, and Friedel-Crafts reactions. We saw that in chapter 16. That's review, right? And we can also react a phenol with strong oxidizing agents to yield a quinone. And Fremy salt also works, but it works through a radical mechanism. So it can be quite challenging and convoluted mechanism. I'm not going to really go into a lot of details about quinones. They are very useful. We see them a lot in nature, and that's why I wanted to point it out to you for those of you who plan to take biochemistry. Ubiquinones, which are in the mitochondria of cells, they help to mediate respiration processes and basically do electron transfer redox reactions in order to produce energy, right, in the body. And you probably will study this in the future if you're going to take biochemistry. And you can see, like in step 1, we have NADH, which is the reduced form, which is oxidized into NAD+. And we use this ubiquinone, to do the reaction under acidic conditions, because we're in the mitochondria there. And then this is the respiration process where we're having oxygen here there's a few more steps here. We're kind of skipping a very simplified form of biochem, right? But basically to give us back our ubiquinone, so it's regenerated, it's like a catalyst in a sense here. And the net change here, as you can see here, this is oxidized, right? And in this case here, oxygen is reduced, or reduction. And this oxidation-reduction reaction actually produces a lot of energy for us. And this happens not only, in humans, but in many different types of living organisms. So it's very important. That's why they're called ubiquinones, because they're ubiquitous in nature. They're very common. And so I wanted to show you that we can kind of mimic it. We can make quinones by oxidizing, with strong oxidizing agents, phenols into quinones. Okay? And maybe you'll see that in your future if you take a more advanced organic chemistry class. I wanted to review briefly over spectroscopy of alcohols and phenols. Remember that there's a characteristic OH stretch for an alcohol around 3,300 to 3,600 wave numbers. It's strong, it's broad, it's really obvious if you have an alcohol or not, okay, in the IR. So that's the first thing I look at when I do spectroscopy is like, is there a broad band in my IR or at that 3,000 wave number? If it is, it's either an alcohol or a amine. If it's very strong, definitely an alcohol. You can sometimes see the OH stretch, the sharp absorption around 3,600. That's where all the CHs show up. But like I said, when you're looking at IR, it's hard to distinguish between, oh, this is a carbon-hydrogen off of an aromatic ring versus a carbon-hydrogen off of off of just an alkyl group, or this is an OH stretch. These kinds of things are not, it's harder to see that kind of sharp splitting there. You would have to sit down for a while to do it. Also, another one you should learn is that the single bond carbon-oxygen stretching absorbs near 1050 wave numbers. So that's going to be characteristic, of a carbon-oxygen single bond, but that could be also an ether, right? Or some type of ester. And phenols, once again, their OHs absorb around the same region, still strong and broad. So you can see here, immediately if I saw this group here, I'm thinking, I have an alcohol in there. That should just be instantaneous, less than a second, you see that. You can look down at 1050 and see a strong, sharp peak that also helps to support that. This is a single bond carbon-oxygen stretch. Phenols will be very similar in their OH band, strong and broad, around 3,000 wave numbers. However, you should also look for the aromatic peaks, one at 1450 wave numbers and one at 1600 that show up to illustrate aromaticity. In addition, you should also look at the fingerprint region to look for what type of substituted phenol you have. Is it mono? Is it di? Is it tri-substituted? If it's di, is it ortho, meta, or para? So there's lots of key information you can get from the IR that we've gone over already in chapters 12 and 13, as well as for aromatic compounds we went over in great detail in chapter 15. So make sure you're practicing your spectroscopy. NMR is a little interesting. The OH, the carbon that's bonded, so for carbon 13, the carbon that's bonded to the OH does absorb at a lower field because it is de-shielded by the electronegative oxygen atom, so it kind of shifts it downfield to 50 or 80 parts per million. Proton NMR, we're able to, and there's a figure, and I will show you in a figure in the next slide too, but there's figures in your textbook to illustrate this, but you're able to see the OH in the proton NMR, but it moves around a lot. Okay, I say 3.5 before, I've seen it all the way up to 5 before. It doesn't stay in place. And it really depends on the amount of moisture or acid in your sample. So when you make an NMR sample, you usually dissolve your sample in deuterated chloroform. But over time, chloroform absorbs water from the air. And so that NMR solvent may contain water, and that will shift your OH around because that OH is exchanging protons with your deuterated solvent. Okay. I also want to point out, because of that phenomenon, we don't see any splitting or spin-spin coupling between an OH and neighboring protons. It's usually just a little broad singlet. But just so you know, spin-spin splitting is observed between protons on the carbon atom, right, and neighbors, but it just won't be split by the OH itself. So in the next slide, I'm showing you propanol. Oh yeah, and the phenol protons, once again, they kind of move around. Same thing. This one here is your OH. And now this is a computer-generated NMR, okay? Normally, this would be short and kind of hard to see. It's usually broader than this. And you notice it's a singlet, right? It's not split by anything, right? So because it's just focused on exchanging protons with the moisture or acid in your sample, right? It's not even going to be, there's not enough time for it to be split. This CH2, therefore, is only a triplet because it's next to two hydrogens. So we can see the CH2, shift it really downfield in comparison to normal CH2s because it's attached directly to the oxygen. This CH2 in green is next to 5 non-equivalent protons, so it's a sextet. So 1, 2, 3, 4, 5, 6. So that makes sense. And then this CH3, which integrates for more protons, larger, is going to be a triplet, right, because it's next to 2 non-equivalent protons. Remember, TMS is your reference. So there's not going to be any splitting between this proton and its neighboring protons, right? Just because of that moisture exchange. And remember, OHs move, so it just depends on the amount of moisture present in your sample, okay? Back in Chapter 12, I talked about mass spectrometry, and more specifically with alcohols undergoing alpha cleavage and dehydration. And we got to practice that a lot with the work session when we did the spectroscopy. So if you feel a little rusty with this is review, then once again, come see me, come ask questions. I'm here to help you. Mass spec is challenging, but you can do it, okay? Alpha cleavage just means that you're cleaving between the alpha and the beta carbon. The alpha carbon is the one that's attached directly to the functional group. So you're going to cleave there, and the way you're going to cleave, the reason why you're going to cleave there is that way you end up with a cation on that alpha carbon so that it's stabilized by resonance. So you're going to make fragments that are stabilized by resonance that can be observed by the mass spec. Remember, mass spec only observes charged particles or fragments. Okay? So we're not going to see this. We're going to see the loss of it, the radical, but we're not going to actually see that peak there based on this alpha cleavage. Dehydration, it's a very high energy process. You're bombarding these alcohols with lots of electrons and just crazy stuff is happening. So many times alcohols will undergo dehydration. So if you see a mass loss for water, which is a mass loss of 18, you definitely know an alcohol was present in your sample. Okay? Those are the two main fragmentation patterns that you need to be aware of for my class for alcohols. And this is just showing you an example for butanol, right? We have the molecular ion peak here. It's really tiny, but it's there at 74, which gives you the molar mass or the molecular weight of your starting material. And then the first fragment we see has a mass loss of 18, right? 74 minus 56 is going to give us a mass loss of 18, and that tells us that we had some dehydration occur. Another fragment you're going to see is going to be alpha cleavage. We see a peak at 31, right? And so we see a huge mass loss that's equal to the molecular weight of this fragment here. And then we get the molecular weight of what's left over of the charged fragments. Okay? So just make sure you're practicing that. There's, remember Chapter 12, great practice problems in the back of the book. I do have a solutions manual, so if you want to check your work, come to office hours or during work sessions, just keep practicing spectroscopy daily. I know it can be intimidating, so you might be procrastinating on it. I don't want to look at it yet, just not yet, Dr. P. I'm not ready for it, but you need to. Don't be afraid, and I'm here to help you out, okay? So we've just finished Chapter 17. Make sure you've read through the entire chapter now, and you're working all those practice problems and asking questions when you need to, or write those questions down and then come ask me your questions later on so I can help you out and so you can master this material. And in Chapter 18, in our next lecture, we're going to continue on studying oxygen-containing functional groups. And That's going to be more about ethers and epoxides, and then we'll get into carbonyl chemistry in Chapter 19. Okay? So good luck studying, and I will see you soon. Take care.